All right, so to begin our discussion of greatest common divisor, I want you to consider this scenario where we have two bands that need to be combined to march together in a parade. So there's a 24-member band that's going to march behind a 30-member band. The combined bands have to have the same number of columns, and each column needs to be the same size. So what is the greatest number of columns in which they can march? The bands could march in two columns because we have a 24-person band and a 30-person band. So we could have two columns for the 24-person band, and they would have 12 people each, and two columns for the 30-person band, and they would have 15 people each. And that would work, and we would have the same number of columns for each band, but that doesn't satisfy that condition of having the greatest number of columns, because we could make the parade wider in a sense. So the number of columns has to divide both 24 and 30. And so we have numbers that divide both 24 and 30 are 1, 2, 3, and 6, and the greatest of these numbers is 6. So the first band would have 6 columns with 4 members in each. It would look like this. So that's the 24-person band. And then for the 30-person band, we would have 6 columns with 5 people each. This is what's called the greatest common divisor, or sometimes the greatest common factor. Those are interchangeable terms of two whole numbers. We define the greatest common divisor of two whole numbers A and B, where they're not both 0, as the greatest whole number that divides both A and B. So we can think about greatest common divisor using a colored rod method. So if we want to find the greatest common divisor of 6 and 8, we would model the 6 with a 6 rod and the 8 with an 8 rod. And our goal is to find out the longest rod that we can use, multiples of that rod to build both the 6 rod and the 8 rod. We can use the 2 rods to build both the 6 and 8 rods. So we would use 3 2 rods to build the 6 rod, and we would use 4 2 rods to build the 8 rod. So we need to determine that 2 rod is the biggest rod we could use to build both of these 6 rod and the 8 rod. We could use the 3 rods to build the 6 rod, but not the 8 rod. And the 4 rods could be used to build the 8 rod, but not the 6 rod. And the 5 rods are too big to build either, because 5 won't divide either 6 or 8. And same with the 6 rods. We can't use it to build the 8 rod, but we could use it to represent the 6 rod. And so the greatest common divisor of 6 and 8 is going to be 2, because that 2 rod is the biggest one we could use to build both the 6 length and the 8 length. Another way we could discuss finding the greatest common divisor is called the intersection of sets method. You list all of the members of the set of the whole number divisors of the two different numbers, and then find the set of all the common divisors. So the intersection of those two sets of lists of divisors, and finally you'll pick the greatest element in that set. So for example, if we wanted to find the greatest common divisor of 20 and 32, we would denote the sets of divisors of 20 by D20 and the set of divisors of 32 by D32. So D20 consists of 1, 2, 4, 5, 10, and 20, because those are all of the divisors of 20. D32 consists of 1, 2, 4, 8, 16, and 32, because those are all of the divisors of 32. And so now I'm going to look for the intersection of these two sets, for all of the divisors that they have in common. So I see that they share 1, they share 1, they share 2, and they share 4 as common divisors. So the intersection of these two sets of divisors is 1, 2, and 4, and the greatest number in that intersection of the sets is 4. So the greatest common divisor of 20 and 32 is 4. Another way we can find the greatest common divisor of two or more non-zero whole numbers is using their prime factorizations of those numbers. So first we would find the prime factorizations of the given numbers and identify each common prime factor of the given numbers. The greatest common divisor is the product of those common factors, each raised to the lowest power of that prime that occurs in any of the prime factorizations. And something to notice is that numbers who have a greatest common divisor of 1 are called relatively prime. So 4 and 9 don't have any shared divisors greater than 1, so their GCD is 1. 4 and 9 are relatively prime. Let's use that prime factorization method to find the greatest common divisor of 108 and 72. So first, I would need to find the prime factorization of 108 and 72. So if I use a factor tree method to do that, of 108, I know it's divisible by 4 because the last two digits are divisible by 4. So 108 divided by 4 is 27. 27 is divisible by 3 because 2 plus 7 is 9, and 9 is divisible by 3. 27 divided by 3 is 9. 9 is 3 times 3. 4 is 2 times 2. So 108 is 2 2's. So it's 2 squared times, and I have 3 3's, so times 3 cubed. And then I need to find the prime factorization of 72. 72 is divisible by 3 because 7 plus 2 is 9, which is divisible by 3. So 72 divided by 3 is 24. 4 is divisible by 3 and 8. 8 is 2 times 4. 4 is 2 times 2. So here, 72, I have 3 2's. So I have 2 cubed, and I have 2 3's times 3 squared. So that prime factorization method tells me that I take each of the prime factors that they have in common. So they both actually have a 2 common factor. So the greatest common divisor will be 2, and then I take the lowest power. So the lowest power I have is a 2. So I have 2 squared times, and then the next common factor that they share is 3. And then the lowest power there is also 2. So I'll have times 3 squared. So that's 2 squared times 3 squared, which is 4, times 9, which is 36. So the greatest common factor of 108 and 72 is 36. Here's that work typed out for us. Next, we want to determine the greatest common divisor of 0 and 13. So because 13 divides 0, everything divides 0, and 13 divides 13, the greatest common divisor of these two numbers is 13 itself. let's consider the greatest common divisor of x and y if we know that x's prime factorization is 2 cubed times 7 squared times 11 times 13, and y's prime factorization is 2 times 7 cubed times 13 times 17. So looking for the greatest common divisor, I want to find first those prime factors that the x and y share in common. So they both share 2, they both share 7, and they both share 13. Then I'm going to look for those lowest exponents between the common factors. So the lowest exponent for 2 is actually a kind of secret 1, right? I have 2 to the first power in my y. When I look at 7, the lowest exponent I have is 2, and again, I have a hidden exponent of 1 in both my 13s, so I would use 1 as the smallest exponent there. So the greatest common divisor of x and y would be 2 to the first power times 7 squared times 13 to the first power. Multiply out and see it would be 2 times 49 times 13, which is 1,274. Another similar example, so again, we have prime factorizations of x, y, and z. So now we have 3 numbers that we're trying to find the greatest common divisor between. So again, I'm going to look for the prime factors that are shared between x, y, and z. So all of x, y, and z have 2 as a prime factor. X, y, and z also have 7s in their prime factorization. But those are all of the shared factors because z doesn't have any more factors, so it can't share any of the other factors. Now I'm going to look for the lowest powers of these factors. So 2 has a secret exponent of 1 in y, and 7 has a secret hidden exponent of 1 in z. So the greatest common divisor of x, y, and z will be 2 to the 1 times 7 to the 1, or 14. And lastly, greatest common divisor of x and y, if x is 5 to the 4th power times 13 to the 10th power, and y is 3 to the 10th power times 11 to the 20th power. We would look for shared prime factors of x and y, but x's only prime factors are 5 and 13, and y's prime factors are 3 and 11, so they don't share any common prime factors, so their greatest common divisor is 1, and we would say that x and y are relatively prime.